Chapter 3 of The Chemistry of Cookery by W. Mattieu Williams. This LibriVox recording is in the public domain. Recording by Nikki Myers from Gettysburg, Pennsylvania. To learn more about me, please visit nikkisessentials.com. Albumen. In order to illustrate some of the changes which take place in the cooking of animal food, I will first take the simple case of cooking an egg by means of hot water. These changes are in this case easily visible and very simple, although the egg itself contains all the materials of a complete animal: bones, muscles, viscera, brain, nerves, and feathers of the chicken. All are produced from the egg, nothing being added and little or nothing taken away. I should, however, add that in eating an egg we do not get quite so much of it as the chicken does. Liebig found by analysis that in the white and the yolk there is a deficiency of mineral matter for supplying the bones of the chick, and that this deficiency is supplied by some of the shell being dissolved by the phosphoric acid which is formed inside the egg, by the combination of the oxygen of the air which passes through the shell, with the phosphorus contained in the soft matter of the egg. By comparing the shell of a hen's egg after the chicken is hatched from it with that of a freshly laid egg, the difference of thickness may be easily seen. When we open a raw egg, we find enveloped in a stoutish membrane a quantity of glairy, slimy, viscous, colorless fluid, which, as everybody now knows, is called albumen, a Latin translation of its common name, the white. Within the white of the egg is the yolk, chiefly composed of albumen, but with some other constituents added, notably a peculiar oil. At present I will only consider the changes which cookery effects on the main constituent of the egg, merely adding that this same albumen is one of the most important, if not the one most important, material of animal food, and is represented by a corresponding nutritious constituent in vegetables. We all know that when an egg has been immersed during a few minutes in boiling water, the colorless, slimy liquid is converted into the white solid which it owes its name. This coagulation of albumen is one of the most decided and best understood changes effected by cookery, and therefore demands a special study. Place some fresh, raw white of egg in a test tube or other suitable glass vessel, and in the midst of it immerse the bulb of a thermometer. Cylindrical thermometers, with the degrees marked on the glass stem, are made for such laboratory purposes. Place the tube containing the albumen in a vessel of water and gradually heat this. When the albumen attains a temperature of about 134 degrees Fahrenheit, white fibers will begin to appear within it. These will increase until about 160 degrees is attained, when the whole mass will become white and nearly opaque. It is now coagulated and may be called solid. Now, examine some of the result, and you will find that the albumen, thus only just coagulated, is a tender, delicate, jelly-like substance, having every appearance to sight, touch, and taste of being easily digestible. This is the case. Having settled these points, proceed with the experiment by heating the remainder of the albumen or a new sample up to 212 degrees, and keeping it for a while at this temperature. It will dry, shrink, and become horny. If the heat is carried a little further, it becomes converted into a substance which is so hard and tough that a valuable cement is obtained by simply smearing the edges of the article to be cemented with white of egg, and then heating it to a little above 212 degrees. This simple experiment teaches a great deal of what is but little known concerning the philosophy of cookery. It shows, in the first place, that so far as the coagulation of the albumen is concerned, the cooking temperature is not 212 degrees, or that of boiling water, but 160 degrees, i.e. 52 degrees below it. Everybody knows the difference between a tender, juicy steak, rounded or plumped out in the middle, and a tough, leathery abomination that has been so cooked as to shrivel and curl up. The contraction, drying up, and hornifying of the albumen in the test tube represents the albumen of the latter, while the tender, delicate, trembling semi-solid that was coagulated at 160 degrees represents the albumen in the first. But this is a digression, or rather anticipation, seeing that the grilling of a beefsteak is a problem of profound complexity that we cannot solve until we have mastered the rudiments. We have not yet determined how to practically apply the laws of albumin coagulation as discovered by our test tube experiment to the cooking of a breakfast egg. The non-professional student may do this at the breakfast fireside. The apparatus required is a saucepan large enough for boiling a pint of water. The materials: 2 eggs. Cook one in the orthodox manner by keeping it in boiling water 3½ minutes. Then place the other in this same boiling water, but instead of keeping the saucepan over the fire, place it on the hearth and leave it there, with the egg in it, about 10 minutes or more. A still better way of making the comparative experiment is to use, for the second egg, a water bath, or bain-marie, of the French cook, a vessel immersed in boiling or nearly boiling water, like a glue pot, and therefore not quite so hot as its source of heat. In this case, a thermometer should be used, and the water surrounding the egg be kept at or near 180 degrees Fahrenheit. Time of immersion, about 10 or 12 minutes. A comparison of results will show that the egg that has been cooked at a temperature of more than 30 degrees below the boiling point of water is tender and delicate, evenly so throughout, no part being hard, while another part is semi-raw and slimy. I said 10 minutes or more because, when thus cooked, a prolonged exposure to the hot water does no mischief, if the temperature of 160 degrees is not exceeded. It may remain twice as long without hardening. The 180 degrees is above named because the rising of the temperature of the egg itself is due to the difference between its own temperature and that of the water, and when that difference is very small, this takes place very slowly, besides which the temperature of the water is, of course, lowered in raising that of the cold egg. In order to test this principle severely, I made the following experiment. At 10:30 p.m. I placed a new laid egg in a covered stoneware jar of about 1 pint capacity, and filled this with boiling water, then wrapped the jar in many folds of flannel, so many that, with the egg, they filled a hat case, in which I placed the bundle and left it there until breakfast time next morning. 10 hours later, on unrolling, I found the water cooled down to 95 degrees. The yolk of the egg was hard, but the white only just solidified, and much softer than the yolk. On repeating the experiment and leaving the egg in its flannel coating for 4 hours, the temperature of the water was 123 degrees, and the egg in similar condition. The white cooked in perfection, delicately tender, but the yolk too hard. A third experiment of 12 hours, water at 200 degrees, on starting, gave a similar result as regards the state of the egg. I thus found that the yolk coagulates firmly at a lower temperature than the white. Whether this is due to a different condition of the albumin itself, or to the action of the other constituents on the albumin, requires further research to determine. The albumin of the yolk has received the name of vitellin, and is usually described as another variety differing from that of the white, as it is differently affected by chemical reagents. But layman regards it as a mixture of albumin and casein, and describes experiments which justify his conclusion. The difference of the temperature of coagulation does not appear to have been observed, and I cannot understand how the admixture of casein can affect it. When eggs are cooked in the ordinary way, the 3½ minutes immersion is insufficient to allow the heat to pass fully to the middle of the egg, and therefore the white is subjected to a higher temperature than the yolk. In my experiment there was time for a practically uniform diffusion of the heat throughout. I shall describe hereafter what is called the Norwegian cooking apparatus, wherein fowls are cooked as the eggs were in my hat case. Albumin exists in flesh as one of its juices, rather than a definitely organized condition. It is distributed between the fibers of the lean, i.e. the muscles, and it lubricates the tissues generally, besides being an important constituent of the blood itself, of that portion of the blood which remains liquid when the blood is dead, i.e. the serum. As blood is not an ordinary article of food, except in the form of black puddings, its albumin need not be here considered, nor the debated question of whether its albumin is identical, the albumin of the flesh. Existing thus in a liquid state in our ordinary flesh meats, it is liable to be wasted in the course of cookery, especially if the cook has only received the customary technical education and remains in technological ignorance. To illustrate this, let us suppose that a leg of mutton, a slice of cod, or a piece of salmon is to be cooked in water, boiled, as the cook says, keeping in mind the results of the previously described experiments on the egg albumen, and also the fact that in its liquid state albumen is diffusible in water. The reader may now stand as scientific umpire in answering the question whether the fish or the flesh should be put in hot water at once or in cold water, and gradually heated. The big Indians and the little Indians of Lilliput were not more definitely divided than are certain cookery authorities on this question in reference to fish. Referring at random to the cookery books that come first to hand, I find them about equally divided on the question. Confining our attention at present to the albumen, what must happen if the fish or flesh is put in cold water, which is gradually heated? Obviously, a loss of albumen by exudation and diffusion through the water, especially in the case of sliced fish or of meat exposing much surface of fibers cut across. It is also evident that such loss of albumen will be shown by its coagulation when the water is sufficiently heated. Practical readers will at once recognize in the scum which rises to the surface of the boiling water, and in the milkiness that is more or less diffused throughout it, the evidence of such loss of albumen. The loss indicates the desirability of plunging the fish or flesh at once into water hot enough to immediately coagulate the superficial albumen, and thereby plug the pores through which the inner albuminous juice otherwise exudes. But this is not all. There are other juices besides albumen. These are the most important of the flavoring constituents, and with the other constituents of animal food, have great nutritive value, so much so that animal food is quite tasteless and almost worthless without them. I have laid especial emphasis on the above qualification, lest the reader should be led into error originated by the Bone Soup Committee of the French Academy, and propagated widely by Liebig, that of regarding these juices as a concentrated nutriment when taken alone. They constitute, collectively, the extractum carnis, which, with the addition of more or less gelatin, the less the better, is commonly sold as Liebig's extract of meat. It is prepared by simply mincing lean meat, exposing it to the action of cold water, and then evaporating down the solution of extract thus obtained. I shall return to this on reaching the subjects of clear soups and beef tea, at present merely adding as evidence of the importance of retaining these juices in cooked meat, that the extracts of beef, mutton, and pork may be distinguished by their specific flavors. Some extract of kangaroo sent to me many years ago from Australia by the Ramorny Company made a soup that was curiously different in flavor from the other extracts similarly prepared by the same company. Epicures pronounced it very choice and gamey. When these juices are removed from the meat, mutton, beef, pork, the remaining solids are all alike, so far as the palate alone can distinguish. Let us now apply these principles practically to the case of a leg of mutton. First, in order to seal the pores, the meat should be put into boiling water. The water should be kept boiling for 5 or 10 minutes. A coating of firmly coagulated albumen will thus envelop the joint. Now, instead of boiling or simmering the water, set the saucepan aside, where the water will retain a temperature of about 180 degrees or 32 degrees below the boiling point. Continue this about half as long again, or double the usual time given in the cookery books for boiling a leg of mutton, and try the effect. It will be analogous to that of the egg cooked on the same principles and appreciated accordingly. The usual addition of salt to the water is very desirable. It has a threefold action. First, it directly acts on the superficial albumen with coagulating effect. Second, it slightly raises the boiling point of the water. And third, by increasing the density of the water. The exosmosis, or oozing out of the juices, is less active. These actions are slight, but all cooperate in keeping in the juices. I should add that a leg of mutton for boiling should be fresh and not hung as for roasting. The reasons for this hereafter. "Please, Mum, the fish would break to pieces," would be the probable reply of the unscientific cook, to whom her mistress had suggested the desirability of cooking fish in accordance with the principles expounded above. Many kinds of fish would thus break if the popular notions of boiling were carried out, and the fish suddenly immersed in water that was agitated by the act of ebullition. But this difficulty vanishes when the true theory of cookery is understood and practically applied by cooking the fish from beginning to end without ever boiling the water at all. In the case of the leg of mutton, chosen as a previous example, the plunging in boiling water and maintenance of boiling point for a few minutes was unobjectionable, as the most effectual means of obtaining the firm coagulation of a superficial layer of albumen. But in the case of fragile fish, this advantage can only be obtained in a minor degree by using water just below the boiling point. The breaking of the fish by the agitation of the boiling water does more than merely disfigure it when served. It opens outlets to the juices and thereby depreciates the flavor, besides sacrificing some of the nutritious albumen. To demonstrate this experimentally, take 2 equal slices from the same salmon. Cook one according to Mrs. Beeton and the other authorities by putting it into cold water and pouring cold water over it, then heating it up to the boiling point. Cook the other slice by putting it into water nearly boiling, about 200 degrees Fahrenheit, and keeping it at about 180 degrees to 200 degrees, but never boiling at all. Then dish up, examine, and taste. The second will be found to have retained more of its proper salmon color and flavor. The first will be paler and more like cod, or other whitefish, owing to the exosmosis, or oozing out of its characteristic juices, when 2 similar pieces of split salmon are thus cooked. The difference between them is still more remarkable. I should add that the practice of splitting salmon for boiling, once so fashionable, is now nearly obsolete, and justly so. I was surprised, and at first considerably puzzled, at what I saw of salmon cooking in Norway. As this fish is so abundant there, 1d. per pound would be regarded as a high price in the Telemark. I naturally supposed that the large experience operating by natural selection would have evolved the best method of cooking it, but found that not only in the farmhouses of the interior, but at such hotels as the Victoria in Christiania, the usual cookery was effected by cutting the fish into small pieces and soddening it in water in such wise that it came to table almost colorless, and with merely a faint suggestion of what we prize as the rich flavor of salmon. A few months' experience and a little reflection solved the problem. Salmon is so rich and has so special a flavor that when daily eaten it soon palls on the palate. Everybody has heard the old story of the clause in the indentures of the Aberdeen apprentices, binding the masters not to feed the boys on salmon more frequently than twice a week. If the story is not true, it ought to be, for full meals of salmon every day would ere long render the special flavor of this otherwise delicious fish quite sickening. By boiling out the rich oil of the salmon, the Norwegian reduces it nearly to the condition of codfish, concerning which I learned a curious fact from 2 old Doggerbank fishermen, with whom I had a long sailing cruise from the Golden Horn to the Thames. They agreed in stating that codfish is like bread, that they and all their mates lived upon it, and sea biscuits, day after day, for months together, and never tired, while richer fish ultimately became repulsive if eaten daily. This statement was elicited by an immediate experience. We were in the Mediterranean, where bonita were very abundant, and every morning and evening I amused myself by spearing them from the martingale of the schooner, and so successfully that all hands, or rather mouths, were abundantly supplied with this delicious dark-fleshed, full-blooded, and high-flavored fish. I began by making 3 meals a day on it, but at the end of about a week was glad to return to the ordinary ship's fare of salt junk and chickens. The following account of an experiment of Count Rumford's is very interesting and instructive. He says, "I had long suspected that it could hardly be possible that precisely the temperature of 212 degrees, that of boiling water, should be that which is best adapted for cooking all sorts of food, but it was the unexpected result of an experiment that I made with another view, which made me particularly attentive to this subject, desirous of finding out whether it would be possible to roast meat on a machine that I had contrived by drying potatoes, and fitted up in the kitchen of the House of Industry at Munich. I put a shoulder of mutton into it, and after attending to the experiment 3 hours and finding it showed no signs of being done, I concluded that the heat was not sufficiently intense, and despairing of success, I went home, rather out of humour at my ill success, and abandoned my shoulder of mutton to the cookmaids. It being late in the evening, and the cookmaids thinking perhaps the meat would be as safe in the drying machine as anywhere else, left it there all night. When they came in the morning to take it away, intending to cook it for their dinner, they were much surprised at finding it already cooked, and not merely eatable, but perfectly well done, and most singularly well tasted. This appeared to them the more miraculous, as the fire under the machine was quite gone out before they left the kitchen in the evening to go to bed, and as they locked up the kitchen when they left it, and taken away the key. This wonderful shoulder of mutton was immediately brought to me in triumph, and though I was at no great loss to account for what had happened, yet it certainly was quite unexpected, and when I tasted the meat I was very much surprised indeed to find it very different, both in taste and flavour, from any I had ever tasted. It was perfectly tender, but though it was so much done, it did not appear to be in the least sodden or insipid. On the contrary, it was uncommonly savoury and high-flavoured. What I have already explained concerning the coagulation of albumen will render this result fairly intelligible. It will be still more so after what follows concerning the effect of heat on other constituents of a shoulder of mutton. The Norwegian cooking apparatus to which I had already alluded, and which is now commercially supplied in England, does its work in a somewhat similar manner. It consists of an inner tin pot with well-fitting lid, which fits into a box having a thick lining of ill-conducting material such as felt, wool, or sawdust. It should be 2 or 3 inches thick, bottom and sides. A fowl, for example, is put into the tin, which is then filled up with boiling water, and covered with a close-fitting cover, lined like the box, and firmly strapped down. This may be left for 10 or 12 hours, when the fowl will be found most delicately cooked. For yachtsmen and camping-out parties, it is a very luxurious apparatus. End of Chapter 3.